Hello, this is Mr. Craig, and I wish to talk about the homework from day 102. This would be Kinetics, technically part C, but it's actually our second homework of this topic. The first problem that was asked here is that it says that the decomposition of hydrogen peroxide was studied and the following data were obtained at a particular temperature. You were given times that were taken throughout the experiment, 0 seconds through 3600 seconds, and then the concentration of the hydrogen peroxide was measured, which was in this column here. You were to go and calculate the natural log of the concentration of the hydrogen peroxide and enter the data here in the last column, and then take all that data and accurately, or as accurately as you could, draw a graph. I know that I looked at some of the graphs, and some of the graphs look better than others. But again, what we were trying to get from this data was somewhat of a straight line that actually went in that direction. So recognizing what type of graph we had here in accordance to what our labels were along the y-axis and along the x-axis can tell us what type of order this reactant is. And in this reaction, it's just the decomposition of hydrogen peroxide, so you only have one reactant. And the question actually says down here, determine the rate law. So the first thing that we want to do is actually not determine the rate law, but determine the reaction order, or the reactant order. And based on this graph that has a negative slope, and the labels are the natural log of the concentration versus time, should tell you that this is a first order reactant. Since we have a first order reactant in our rate law, again, the rate law is something that we did in the last homework, and a lot of students were confused about what the rate law actually was. Make sure you know what the rate law is, because you will be asked to write a rate law on the AP exam. So the rate law, again, is the rate, the word rate, and we can't do anything with the rate in this equation because we don't know anything about the rate itself, nor do we care. The K is a constant. We'll do something with that here in a moment. But this right here is what we do care about, and we'll put the order, actually in this case here, as a first order reactant. So this is our rate law right here. This is the sentence that tells everybody what the K is, the constant. If we had a rate, what it could be. If we know the K and the concentration of hydrogen peroxide, we can determine the rate based on that information. But the question didn't ask us to do that. So we have the rate law, we have the reaction order. Again, is a first order reactant since there is only, a first order reaction since there is only one reactant. The value of the rate constant, well, what we need to do is use the equation that we had. And what we want to do is we want to pick a coordinate that is as close to the beginning as possible without being zero. In other words, we don't want to have a concentration that's zero. We don't want to have a time that's zero, or a natural log value that's zero. That just is bad math. So our first opportunity to actually plug in some good data is at 2 minutes or 120 seconds. So what we'll want to do is actually plug that values in there. So again, it's how much remains. So at this point here, we started off with 1 molar and now we're down to 0.91. The equation states that the concentration at a given point in time, that's what that top value is, over what we started with, which is the 1 molar. And we're looking for the K here, so we want to plug in our time. Rearrange the equation so we can solve for K. And again, what I did was I took that negative sign that was with the 120 and brought it over here so we could get an actual value for K that's not negative. If you left that negative over here with the negative K, then you would have a negative number. So negative K is equal to the negative slope. There's nothing wrong with stating that, just don't write K is equal to a negative value. K is our slope, but it is a negative slope, so that's why we have this line that goes in that direction. Alright, the concentration at 4,000 seconds was the last question. So we know that the concentration of the hydrogen peroxide decreases as time increases. So we should have a value that's less than this when we get to our answer for 4,000 seconds. So what we want to do is we now have our rate constant K, and We are looking for the concentration of hydrogen peroxide, so we do not know what that is. We do know that we started with a 1 mole solution. We do know that we have a natural log function here, and we do know K, and we do know time. So what that means is we need to multiply K times the time, and in that case here we get this value right here. And notice that there is no unit, because with the K it's 1/seconds, time is seconds. So what we want to do is calculate the concentration of the hydrogen peroxide, but it is not a negative 3.14. That's the natural log of the hydrogen peroxide. Now when we come up to our chart, and I didn't ask you to do this, but it would be a good idea to put that value in there, negative 3.14. And that does seem like a reasonable answer, because as time goes forward, the natural log of the concentration of hydrogen peroxide becomes more negative. So a negative 3.14 would be a good number to have in this spot right here. So we're on the right track. Now, to get rid of the natural log function, we need to take the anti-natural log on both sides. That's what this equation here is doing. So some of you have had natural logs and anti-natural log. If you haven't, definitely ask me how to do that. I have no problem with showing you this on the calculator, and I can't remember if we did it when we were working with the regular base 10 logs. But we need to get rid of that function. So if I take the anti-natural log of the natural log function, it gets rid of that. So now we have, and we do that to both sides. So if I take the anti-natural log of negative 3.14, I come up with this number right here, the 0.0431. And what's nice about that is we now have gotten rid of the natural log function. We're left with the hydrogen peroxide, and we have a concentration of 0.0431 molar. Now again, checking for whether or not that's a reasonable answer. The concentration should decrease, and yes, 0.0431 is a reasonable answer there. Alright, let's look at number 2. It says a certain first order reaction is 45% complete in 65 seconds. Again, the wording is College Board specific, AP exam type question. Yes, I think they are trying to trick you. I think they're trying to get you to plug in the 45% or the 45 there. Do realize that this concentration where it says A sub T is the concentration that remains. So if you need to write this out right here, it's probably not a bad idea. Take an extra 10 seconds just so you don't mess the whole problem up. We know the time, which is 65 seconds, so that's our time here. We always have to find the K first. So whether you read this question and say, oh, well, I'm looking for the half-life, make sure you find the K. You have to know K before you can do anything else. So we'll calculate K by rearranging the variables here. So now we have our constant, which is right here. And then once we have our constant, then we can simply find the half-life by taking the natural log of 0.5, because again, this is 55% that's here, but half-life is half of the original amount divided by the negative K. So in this case, it should be 75.3 seconds. Question number 3 says a certain reaction has the following form, and again, we have one reactant, and it's a very generic equation here, and it forms one product. And again, the lowercase letters here represent coefficients, but remember, we never ever care about coefficients when we're working with kinetics. The only time we care about coefficients is when we're doing equilibrium. So don't mix those two up. Don't be concerned about, well, what is the coefficient? How are we supposed to do this if we don't know the coefficient? Don't look at the coefficient, please. Alright, so it says that a particular temperature, concentration versus time data was collected for this reaction, and a plot of the natural log of A, that's a very big hint, versus time resulted in a straight line with a slope value of negative 6.9 times 10 to the negative 2. Based on that information right there in word form, not a picture, but in word form, you should recognize that that is a first order reactant. You have to know what the plots are when the straight line is generated. For a zero order reaction, a first order reaction, and a second order reaction, you must know how the straight line is formed. And in this case right here, the natural log of A versus time yields a slope with a value of a negative value. So that means that we have a first order reactant. So now that we know that we have a first order reactant and we only have one reactant, then our rate law should look like this. Again, the rate law should always include the word rate. And that's equal to our constant, which we do not know yet, times the concentration of our reactant. And again, never, ever, ever put products in your rate law. We don't care about products. And the 1 is optional. Whether you want to have a 1 there or not, that's up to you. And again, I just put a note on here simply to be able to recognize either in picture form or word form that if you have a graph that's natural log of A versus time yielding a negative slope, first order. So now that we know it's a first order reaction, or the rate law, and we know it's a first order reactant, then we can go determine the value for the rate constant. You don't need to do a calculation for this, which is very cool. Since we know that the slope value is negative 6.9 times 10 to the negative 2, that's our K. That's our slope. Even back here in question number 1, that's our K. If you can determine that slope, you know K. Okay? So the slope is K. And so since we know what K is, and notice here I have, you can either go negative K is equal to the negative number, or K is that value there. So yes, I agree, it does have a negative slope on the graph, but also it does represent a negative K. Finding the half-life, now that we know what K is, and we know that we have half the concentration of the original amount, plug the values in and solve for T. And so once we have that, we find out that we have 10 seconds. Part C, it says that 87.5% is consumed, while 12.5% remains. I believe you have to calculate that on your own. So plugging those values in will yield 30.1 seconds for this reaction. Number 4. Says a first order reaction is 38.5% complete in 480 seconds. Again, calculate the rate constant. So again, you know that you have a first order reaction. So we have to use the equation that's for a first order reactant. 38.5% complete means that we still have 61.5% remaining. So that has to be the value that goes up top for the A sub T. Again, always start off with one more solution if you want to make life easier on yourself. Then go ahead and calculate this. K yields a 1.01 times 10 to the negative 3 per second. Half-life, again, plug in half the concentration over the negative K value, and in this case it should produce a 6.84 second reaction. And then in part C, 25% consumed should be around 285 seconds, and 75% consumed means that we have 25% remaining, which means that most of the reaction has been completed, so it's around 1373 seconds. And then the very last question where it says 95% is consumed, that means that we have 5%, therefore this should be a lot of time, and in this case it's 2,966 seconds. I hope this has helped. If you have any questions, do not hesitate